Unit 3 is going to start with intermolecular forces. Unit 2, we talked about intramolecular forces, which were bonds, covalent and ionic and metallic. In Unit 3, we're going to talk about the forces from molecule to molecule, forces between molecules, which are intermolecular forces. There are 3 types of intermolecular forces. The first one is London dispersion forces. Sometimes abbreviated LDF. And London dispersion forces are forces between molecules that are due to temporary dipoles.
We're going to learn about dipoles and stuff more.
So, temporary dipoles. If we talk about dipoles, we're talking about a polar molecule due to polar bonds. That's what a dipole is. Temporary dipoles are induced in non-polar molecules and polar molecules because electrons are in constant motion. So if we look at a molecule like diatomic chlorine, diatomic chlorine would be considered non-polar because these 2 atoms have the same electronegativity, so neither one of them is going to pull harder on the electrons than the other. So a non-polar molecule, it has 7 valence electrons, but 17 total electrons. I'm going to draw all the electrons in here once. Each one has 17, 34 total electrons in diatomic chlorine. And because it's nonpolar, we would say that those electrons are evenly distributed. Neither atom is pulling harder than the other. But electrons are in constant motion, right?
Yes.
And as long as things are in constant motion, doesn't it make sense that at any given time, there could be more electrons on this side than this side? Just like out in the hallway during passing period, at any given minute, there could be more students in E hallway than W hallway. And then in the next minute, there could be more in W than E. Because you all are in constant motion. Same thing here. The electrons are constantly moving. And if I could freeze time and look at the electrons, it's likely that at that given second, there would be more on this side than this side. And then the next second, there could be more on this side than this side. Those are temporary dipoles. And temporary dipoles produce a negative side and a positive side. Partial negative, partial positive. Now, these are continuously changing and switching. But as long as it's happening in the molecules in a container, they're going to stick together because you could then have another chlorine molecule with a partial positive that comes next to the partial negative. And those 2, for that instant in time, will be attracted to each other because opposites attract. Negative attracts positive, positive attracts negative. This attraction between these 2 molecules That is an intermolecular force. That is a London dispersion force.
Do we have to know like which is stronger than the other?
We're going to talk about that today. So, London dispersion forces occur in nonpolar molecules. But it also occurs in polar molecules. Just because a molecule is polar doesn't mean that the electrons aren't moving, and you might not have a temporary induced dipole. But this is the only one that occurs in nonpolar molecules. All right.
So like, if they're in like a group, would like they be in a constant state of motion because they're pushing and pulling all the time?
All the time. The next one is dipole-dipole. And this is due to permanent dipoles. Okay, so hydrochloric acid, is this a polar molecule?
Yes.
Yes. One of them is more electronegative than the other. Which one? Chlorine is more electronegative. So the electrons travel towards chlorine. They get pulled towards chlorine. And this side becomes partially negative permanently. And this side becomes partially positive permanently. And if you have a container full of hydrochloric acid, the negative side of one will be attracted to the positive side of the other. And they'll form a dipole-dipole interaction. Here's where we have to be careful, though. So if I ask you what type of intermolecular forces exist in hydrochloric acid, you would tell me that there are dipole-dipole forces because you would understand that it's polar. But you would also have to tell me that there are London dispersion forces because there are still electrons and they're still moving and there are still temporary dipoles being formed in addition to the permanent dipole. So all molecules have London dispersion forces. Nonpolar molecules only have London dispersion forces. Polar molecules have dipole-dipole and London dispersion. You have to list them all. Yep.
So with dipole and dipole, it's just a matter of like how negative it is, not if it's negative?
No, dipole-dipole, if there's a dipole, if it's a polar molecule, it has dipole-dipole.
Yeah, so like if you're like then taking into consideration London dispersion, like you wouldn't say that chlorine is ever positive, it's just either more negative or less
Yes.
negative.
Yep. Okay, the last one is hydrogen bonding. And this is a special type of dipole-dipole. With H bonded to N, O, or F. What's special about N, O, and F?
They're very electronegative.
They're the most electronegative. So if we look at hydrofluoric acid, HF, fluorine chlorine is the most electronegative. It is very good at attracting electrons. So when it makes this covalent bond with hydrogen, it's pulling hydrogen's electron towards it very efficiently. It's very good at it. It's so good at it that it almost completely pulls it off of hydrogen. Not completely, but almost. And when hydrogen gets its one single electron pulled away, all that's left behind is an exposed, very positive nucleus. And that very exposed nucleus makes this partial positive side and this partial negative side extreme, to where hydrogen bonds are stronger than dipole-dipole. If we're comparing apples to apples, and we'll talk about that later. So hydrogen bonds are just special, strong dipole-dipoles with H bonded to N, O, or F. That's all I'm missing. Questions so far? Yep.
Is there a way to express something that's more partial than something else?
No, you just have to understand that it is. Okay, so all of this means that we're going to have to decide if something is polar or not, a molecule is polar or not, so we can assign the types of intermolecular forces. So, how to know if a molecule is polar. Okay, it's understood if all of the bonds are nonpolar, then the molecule is nonpolar. But something can have polar bonds and still be a nonpolar molecule depending on the direction of the dipoles. So CCl4 is an example. If we draw it in something close to what its shape would be, tetrahedral, it doesn't have to be perfect, just do your best in drawing the shape. We have to assign polarity to the bonds. Are these bonds polar, C to Cl?
Yes.
Yes, because one of them is more electronegative. Which one?
Cl.
Cl. So all of these bonds have a dipole pointing towards the chlorine.
What is a dipole?
A dipole is a polar bond. It shows electron motion. The electrons are moving towards the chlorines. Okay, so polar bonds, but is this molecule polar?
No.
No, because the dipoles cancel. They cancel each other out. For those of you who have had physics, this is like vectors.
It's like equilibrium.
It's like equilibrium. The vectors in this case are canceling. If you haven't had physics, think of tying 4 ropes to carbon and having 4 people pull in these directions with equal force. Is carbon going to move? No. If you decide carbon won't move, this is a non-polar molecule. Polar bonds in a non-polar molecule because the dipoles cancel. So what type of intermolecular force would CCl4 have? Only London dispersion. But just because it only has London dispersion forces does not mean that that's a weak London dispersion force. Big molecules with lots of electrons like CCl4 can have lots of temporary dipoles. and lots of temporary dipoles leads to fairly strong intermolecular forces. And we're going to talk about later, therefore, fairly high boiling points and things like that. Questions? Okay. What about this one? Step 1. Decide if your bonds are polar, yes or no?
Yes.
Yes. Towards
Tin.
nitrogen. Nitrogen is more electronegative. Do those dipoles cancel?
No.
No. The general direction is up. So my overall dipole for nitrogen, my polar molecule, NH3, is this side of it is negative, and this side of it is positive. This is a polar molecule. Overall, this side is more negative than this side. So what type of intermolecular forces would I have?
All three.
Both.
All three.
Oh.
Everything has LDF. If it's polar, it's dipole-dipole.
And it's hydrogen.
And it's H bonded to N, so that's hydrogen bonding. Questions so far? Okay. Intermolecular forces and the strength of those intermolecular forces tells us a lot about the properties of a substance. IMFs is intermolecular forces. Stronger IMFs lead to higher boiling and melting points. Okay, so I have this beaker of water. Is water polar?
Yes.
Yes.
Yes, towards oxygen. So I have partial negative, partial positive, partial negative, partial positive. The opposite sides, the positive is attracted to the negative. And we have intermolecular forces from molecule to molecule. The strongest of those three being hydrogen bonds. if I have liquid water and I want to boil it, the amount of energy it's going to take to boil it is directly related to the strength of this intermolecular force, the strength of that hydrogen bond. Stronger bond, higher melting or boiling point. So, I put my beaker of water on a flame, whatever, hot plate. I add energy until I overcome that intermolecular force. I pull the water molecules apart. Once they've been pulled apart, they're able to escape, and they escape into the atmosphere, whatever.
So what does the boiling point increase if there is more water, or is it just
Well, yes,
Longer to heat up.
yes, but
it's a higher temperature or more energy?
more energy overall. The boiling point doesn't change.
Okay.
Boiling point is the boiling point because you're making water escape. You're overcoming intermolecular forces. Okay, so you break this intermolecular force. You do not break bonds. You break intermolecular forces. That's a misconception. Just because it's called a hydrogen bond doesn't mean it's a bond. Bonds are inside molecules. On the AP test a few years ago, there was a question where they gave the students a diagram, and it had some liquid water molecules like this, the Mickey Mouse heads, in the bottom. They were all just sitting at the bottom. And this was before, and then they said add heat. And they were supposed to draw what it would look like after for a point.
That's kind of broad.
Many, many, many students drew this. And they didn't get the point. What happened from here to here? Is this overcoming intermolecular forces? No, this is breaking bonds. When you boil water, you create water vapor, water gas. You do not create hydrogen gas and oxygen gas. It's not this. You make water gas. They wanted just to show that they separated. They turned into gas. That's like a very common misconception. AP students, regular adults in everyday life believe when they boil water, they are making hydrogen gas and oxygen gas. The stuff above the pot on the stove is hydrogen and oxygen. If that were the case, people with a gas stove with that open flame would cause explosions every time they made macaroni and cheese.
Yeah, how does like two highly flammable gases turn into a thing that like is the opposite? Of
Stability, entropy. We'll talk about it later.
like this unit?
No.
Oh.
But the whole point is you are overcoming intermolecular forces. You are not breaking bonds. Breaking this bond takes an incredible amount of energy. That's called hydrolysis, requires an electric current. This it's a little bit of energy. It just requires heat. So just understand the difference between breaking bonds and overcoming intermolecular forces. They're two different things. All right, the last thing I want to talk about to bring all this together is the strength of these things and how we can compare them. So if we look at group 17, the halogens, The first one is fluorine. It has 7 valence electrons, but 9 total, so I'm going to put the inner electrons in there. Fluorine, room temperature, solid, liquid, or gas?
Yes.
Gas. What type of intermolecular force is present here? LDF only. Fluorine is a non-polar molecule. Underneath it, chlorine, 7 valence electrons, but 17 total. Chlorine, room temperature, solid, liquid, or gas?
Yes.
Gas. Not to be confused with the liquid chlorine you put in your swimming pool. That's this stuff dissolved in liquid. That's why whenever you dump it, it's really fumy because the chlorine is escaping. That's why it burns so bad if you accidentally breathe it.
That's just
Don't do that.
Breathing in, accidentally breathing in chlorine gas.
Not a good idea. The next one. Bromine. 7 valence electrons, but 35 total.
never seen bromine, so I don't know. I'll go with gas though. I'll take a guess and go with gas.
Bromine, room temperature,
Gas.
Solid.
liquid.
Aqueous.
Not aqueous, liquid. Difference.
Dang it.
What type of intermolecular forces are present? Just London dispersion forces.
What the heck?
But why is it a liquid at room temperature if it has these weak London dispersion forces?
Stability.
Because it's bigger.
It's so big.
It's big.
That's all.
Big molecules with lots of electrons have lots of LDFs over and over and over again. To the point where those LDFs become strong enough that the boiling point is high enough that this is a liquid at room temperature. LDFs can be strong if the molecule is big enough, if it has enough electrons.
Are there any solid noble gas?
Iodine?
Oh, here we go. No, iodine's a liquid.
You just shook your head no.
So iodine has 53 electrons.
Have you seen? Remember we used iodine? Use that in an experiment? He said, don't get this on your clothes. That's never paid attention.
I'm not drawing the other one because I'm tired of it. But iodine, room temperature,
Liquid.
Solid.
solid.
Gosh dang it.
You're thinking of potassium iodide.
I don't know, Mr. Wilkinson gave me this thing and he said iodine or something and he said don't get it on your clothes.
If you go to the doctor and they put the brown stain stuff on you on like your cut or before they do stitches or something, that's iodine solution. They've dissolved the solid iodine in something. But regular just iodine at room temperature is a solid. What type of intermolecular forces? LDF only. What's water at room temperature?
Liquid.
Liquid. But it has hydrogen bonding. The hydrogen bonds in water are weaker than the LDFs in iodine because it's small. This huge molecule with all these electrons can have strong intermolecular forces that are simply LDF. So for me to say LDF is the weakest, dipole is in the middle, and hydrogen bonding is the strongest, that's not true. It depends on the size of the molecule and other things. On the AP test, I will never ask you which is the strongest. But I might give you 2 molecules in their boiling point and ask you which has stronger intermolecular forces and to list them. It's just understanding the difference. So here, gas, gas, liquid, solid. The size of the electron cloud matters. Bromine and mercury are the only two on the periodic table that are liquids at room temperature. Everything else is either a gas or a solid. Alright, you have one worksheet. It's like the chemical something number 2. No homework tomorrow. It's a work day. Unless you're taking the PSAT, then just take the day off. If you're at home, work on the worksheet. I'll see you Thursday.
Can't wait to see you then.